We take the initial value problem dy by dx is equal to fxy, and this is on the interval from a to b, and the initial value is y at x point 0 is equal to y0. This is an initial value problem with a differential equation plus initial value. We want to solve it numerically. So for that one we define a mesh on an interval. So that's our x-axis. We divide it from a to b into sub-intervals. So these points are known as mesh points: x0, x1, x2, x3, x4, so on. These are our mesh points. And we are having here, on these mesh points, we are going to calculate the numerical solution. These points also are called nodes. So there is a distance, equidistance between these mesh points. A regular mesh point, we say the distance is equal. If distance is not equal, in some of the problems, we say irregular mesh point. But here we are going to take the regular intervals. So our h, the interval, is equal to delta x. And this is equal to xn minus 1 minus x. This is the distance between two adjacent points, which is same as x1, x0, x2, x1 is same. It's also all are equal to h. So yn is approximated value of y at x, we say here y at xn. So we write this one as here y at xn. So this is the value of the yn, we say approximate value, and yxn is our exact value at x equal to xn. Interval a, b we subdivide into n intervals of equal length as said. So n we say that's equal to b minus a over h. So you can see it here, if n is increasing, or we say then h is decreasing. Now we say here, we say h is equal to b minus a over n. When you give me n, I give you the value of h. We say we want to find the number of points, increase the number of points where we want to find the value of the function, unknown function. Then it means our h is going to decrease. When we increase h, then y is going to, n is going to decrease. xn is equal to x0 plus nh. For example, I take n equal to 1, then I will get here the value of x0 plus h. When I take the value of x2, so my x2 is equal to x0 plus 2h. My x3 will be equal to x0 plus 3h. So you can see here, this is my x1, this is my x1, we have just x0 plus h, x2 is x0 plus 2h, x3 is x0 plus 3h. So that's how we can just define this one. As I told in the introduction that our Taylor series is the main key point in our whole discussion of the numerical method. So I just explained to you, we're having the Taylor series for any function y equal to x at point x equal to a. We say yx is equal to y of a plus y dash of a, x minus a over 1 factorial, y double dash of a, x minus a whole square by 3 factorial, y triple dash of a, x minus a whole cube by 3 factorial, and so on. We get x minus 8 power 4, x minus 8 power 5, x power 8 power n. We take all other terms. So here this is actually defined about x equal to a. So x equal to a is the interval about x equal to a is a minus h, a and h. H is the x minus a is equal to h. That's the length of the interval. So if we take x minus a equal to h, so we can just write here that our equation become y of x is equal to y of a plus y dash of a h over 1 factorial. 1 factorial is equal to 1. We can just replace 1 factorial by 1. And we get here at x double dash of a plus h square by 2 factorial plus x triple dash of a, h3 by 3 factorial, and so on. We have, if h is equal to x minus a, then we can write our x is a plus h. So we change in our equation, instead of a we write, instead of x we write a plus h. So I can rewrite this one, the above equation. We can write y a plus h is equal to y of a plus y dash of a h plus y double dash of a, h square by 2 factorial, y triple dash of a, h cube by 3 factorial, and so on. So we replace a by x. We can just change it, and then the interval become x minus h, x plus h. Our interval is h. Here is x minus h, add h, we get x, then add h, we get here x plus h. So we say here that we can just replace the above equation here in this equation, our x by our a by x. So we get here equation in x, y, x plus h is equal to y of x plus y dash of x, h plus y double dash of x, h square by 2 factorial by triple dash of x, h cube by 3 factorial, and so on. Here h is very, very small. We say x going to 0. That's the definition of x. The x is going to 0, it's become very small. For example, I take x h equal to 0.1. So we have h square is will be 0.01, h cube will be 0.001, h4 will be 0.001. So it's become very small. So on this idea, we say that we can just neglect the small terms and we can just work with 2 or 3 terms to power, for example, power h or power h square of the order. So when we increase the order of the Taylor series, our numerical method becomes superior. That's the error become decreasing. So number of terms we are going to increase taking in our Taylor series. Then but here the difficulty will be the derivatives of the function y double dash, y triple dash, y 4 dash. But anyhow, we will get the improvement in the method. So in principle, we say that we neglect the high powers of h, and that's how we define our methods.